LVM is the storage abstraction layer between your file systems and your physical disks. It turns rigid partitions into a flexible three-tier hierarchy that you can reshape on demand. At the top sit logical volumes, or LVs, the virtual block devices that your operating system actually mounts. To extension 4 or XFS, an LV looks indistinguishable from a raw partition. A clean, contiguous range of sectors. But underneath, nothing is fixed. You can grow them, shrink them, rename them, or snapshot them, all while the file system on top stays online. The middle layer is the volume group, or VG. A VG is a pool of capacity carved from one or more underlying physical disks. It is the abstraction boundary where physical storage stops being physical and starts being a bucket of extents you can carve up however you like. At the bottom are the physical volumes, the disks, partitions, or RAID arrays themselves, once they have been initialized with an LVM metadata header. These are the real storage hardware, and LVM sits on top of them as a thin software veneer. So why does LVM exist? For reasons. First, online resize. You can extend or shrink logical volumes with lvextend and lvreduce without unmounting the file system. Second, transparent spanning. A single file system can stretch across multiple disks, as if they were one big drive. Third, cheap point-in-time snapshots using copy on write, perfect for consistent backups. And fourth, striping and mirroring built right in, giving you performance and redundancy without juggling separate RAID controllers. Underneath all of this sits the DM mapper, the Linux device mapper kernel module. LVM is not magic. It is a user space tool that talks to this kernel framework, which builds virtual block devices by mapping logical sectors onto physical sectors. You can see it register itself in /proc/devices under the name device mapper. Finally, how does all this surface in /dev? When you create /dev/vg0/root, what the kernel actually exposes is /dev/dm0. The path /dev/mapper/vg0, root is just a friendly symlink that points to it. The kernel identifies every block device by a major and minor number pair. For device mapper, the major is always 253, and each virtual device gets a unique minor underneath it. That is how your file system finds its way to the right slice of capacity inside the volume group. Every LVM2 administrator needs a safe, read-only toolkit for peeking under the hood. The commands will cover never write to disk, never resize anything, and never alter your volume layout. They only report. Think of them as X-rays for your storage stack. First up, PVS. It prints a compact column-aligned table of every physical volume on the system, showing the device path, its volume group membership, total size, free space, and metadata format. A blank VG column means the PV hasn't been assigned to any volume group yet. Next, VGS. Same idea, one level up. It summarizes each volume group with its name, the count of member physical volumes, the count of logical volumes carved from it, aggregate size, and free space. This is the fastest way to see how much room is left in any VG. Then LVS lists every logical volume with its parent VG, the verbose attributes field, and size. The attr column encodes open status, writability, and allocation policy in a compact code like YAO, letting you read the LV's state at a glance. When you need the full story, pvdisplay dumps every detail of a single physical volume. Its UUID metadata version, physical extent size, total and free PE counts, and which VG it belongs to. It's verbose on purpose, built for deep inspection, not quick scanning. For volume groups and logical volumes, pvdisplay and lvdisplay do the same thorough job one level higher. They reveal internal extent mappings, how many physical extents back each logical extent, allocation policy, and the full chain from LV down to PE. Finally, 3 supporting commands: pscan, vegscan, and lvscan. They walk the system, rediscover LVM metadata on block devices, and rebuild the kernel's in-memory cache. Run them after plugging in a new disk or when the device cache looks stale. They touch only the cache, never the disks. Here's the safety note written in stone. Every command on these cards is inspect only. None of them resize, move, create, or delete anything on your disks. Run them with confidence on production systems, on failing disks, on borrowed machines. They're your safest tool in the LVM2 toolbox. Before touching anything, the safest move is to inspect LVM state with read-only commands. We'll check whether the LVM2 tools are installed, list any physical volumes, volume groups and logical volumes present, and finally confirm the kernel-level device mapper is active. First we confirm the LVM2 userland tools are installed by asking which the LVS binary resolves to. If LVM2 is missing, the fallback message prints so we know to install it before continuing. Next we list any physical volumes with PVS, which reports each PV along with its size, free space, and the volume group it belongs to. The error stream is silenced, so an empty system simply produces no output rather than a confusing error. With VGS we see the volume groups that aggregate those physical volumes. Each row shows the VG name, how many PVs and LVs it contains, and its overall size and free space. LVS drills one level deeper, listing every logical volume inside each volume group, its size and its allocation state. This is the layer applications actually mount as file systems. Now we peek inside /dev/mapper, where the kernel exposes the actual block devices backing each logical volume. The first entries are control nodes and the DMN block devices that LVM2 created. Finally, we confirm the device mapper itself is present in the kernel by grep/proc/devices for its character major number. A hit here proves DM mod is loaded, and the LVM stack has its kernel half in place.